Hello everyone, my name is Tuan, and I am a former master's student at the University of Arkansas. Today, I will be presenting my paper at CVPR 2025, entitled HyperGLM, HyperGraph for Video Scene Graph Generation and Anticipation. This work is supported by the National Science Foundation, and I would also like to thank the High Performance Computing Center for providing GPU resources. In this work, I introduce HyperGLM, a novel approach that integrates multimodal large language models with the Scene HyperGraph to enhance reasoning capabilities for both seen and unseen videos. Traditionally, video scene graph generation methods rely heavily on pairwise connections between objects. While this has been effective to some extent, it inherently limits the model's ability to higher-order relationships and reasoning. To address this limitation, we introduce a procedural graph that models causal relationships. This procedural graph enables our system to anticipate future interactions by understanding patterns and causal links from past interactions within the video. Our approach uniquely integrates two key components: entity scene graphs and the procedural graph. The entity scene graphs capture spatial relationships between objects in each frame, while the procedural graph models their causal transitions over time. Together, they form a unified hypergraph that provides a comprehensive representation of the video scene. Let me illustrate this with an example. Here, the hypergraph combines the entity scene graph, which tracks interactions like picking up, holding, opening, and reading a book, with the procedural graph that models the causal chain of these actions. Additionally, it captures intermediate interactions, such as holding and placing a glass. This integrated hypergraph effectively represents the sequence and causality of actions within the video. Now, let's explore how our hypergraph seamlessly integrates with large language models. The process begins with the image encoder, which processes each video frame to extract rich visual features. These features are then passed through the MLP projector, transforming them into a suitable format for further analysis. Next, the temporal aggregator takes these transformed embeddings, comprising spatial tokens across all frames, and compresses them over time. This step captures the temporal dynamics, ensuring that the model understands how interactions evolve throughout the video. Following this, the MLP projector further transforms these visual embeddings into the language feature space, generating frame tokens that are interleaved with language tokens. Finally, all tokens, including the frame tokens derived from visual data, the language tokens from task queries, and the structured information from the unified hypergraph, are fed into the large language model. By embedding the hypergraph within the token sequence, the language model can leverage this rich, structured data to generate more accurate and contextually relevant answers. This integration enhances the model's overall reasoning capabilities, enabling it to perform advanced analysis and anticipation based on the complex interactions captured in the hypergraph. Here are some qualitative results showcasing our HyperGLM approach. Notice how it accurately models interactions between objects, such as a laptop and a chair. Additionally, it effectively answers user prompts by understanding and anticipating the dynamics of the scene, demonstrating its enhanced reasoning capabilities. As the number of objects and interactions in a video increases, especially in dynamic and changing environments, maintaining accurate relationship modeling becomes increasingly challenging. Our HyperGLM approach excels in these complex scenarios. For instance, it successfully tracks rapid interaction changes from sitting to picking something up, then leaning on a pillow while lying on a mattress, and using a laptop. By effectively modeling these swift and varied interactions, HyperGLM provides precise and contextually relevant answers to user prompts. In conclusion, our approach uniquely integrates entity scene graphs with the procedural graph to form a unified hypergraph. This hypergraph adeptly captures the spatial relationships between objects while simultaneously modeling their causal transitions over time. By embedding this unified hypergraph into large language models, we enhance their ability to reason about multi-way interactions and higher-order relationships within video content. These innovations collectively advance the video scene graph generation and anticipation field, paving the way for more sophisticated and accurate video understanding. That concludes my presentation. Thanks for watching.